Welcome to Ask and Learn.
We want to sketch the curve y is equal to the square root of 1 minus x squared all over x. So in this chapter, they give us this laundry list of steps that we should follow anytime we want to sketch a graph. So let's just go ahead and follow those. So the first thing is they tell us to determine our domain. So this might take a little bit of space, so let's do this on a new page. So 1 minus x squared over x. So there's two things we need to make sure of. We need to make sure that our denominator is not equal to 0, and we need to make sure that the inside of our radical is greater than or equal to 0. So at least we know x, or let me put that in blue. So we at least know x just can't be 0. And to find the rest of our domain, we can go ahead and find where 1 minus x squared is strictly larger than 0. So doing this would give 1 strictly greater than x squared, and we can do -1 square root of, not -1 on that side, but +1 less than x less than -1. So we square root each side and then just put the negative. All right, so from these two things, since this here tells us all the values that x can be, and we know x cannot be equal to 0, so we'd just remove that, and we'd get -1 to 0, union 0 to 1. All right. So our domain ends up being -1 to 0, union 0 to 1. The next step is to find our intercepts. So x-intercept is when we set the function equal to 0. So we'll have 0 is equal to 1 minus x squared square root all over x. And remember, the denominator can never make the function equal to 0. So we would do 0 is equal to the square root of 1 minus x squared. So we square root each side, add the x squared over, and take square roots again, and we'd get x is equal to plus or minus 1. And since 0 is not included in our domain, we know we will not have a y-intercept, so we don't need to solve for that. So now symmetry. Well, any kind of rational function like this, we don't really normally think is going to be periodic. So let's check what f of -x is to see if this function is even or odd. So we're going to have square root of 1 minus, so -x squared. Well, squaring a negative is just going to be positive, so that will just be x squared all over -x. So notice that this here is equal to negative f of x. So we know our function is going to be odd or has symmetry about our origin. So we might be able to use this to help simplify some parts and skip a couple of steps as well. All right, the next thing they tell us to look for is asymptotes. Well, we know we're not really going to have any end behavior as x goes to infinity or negative infinity, since we're bounded between -1 and 1 for our domain. But we do have a horizontal asymptote since when I plug in, or a vertical asymptote, since when I plug in 0, the denominator becomes 0. So let's go ahead and look at what happens as, so the limit as x approaches 0 from the right at first. So f of x, I don't know why I changed that to black, so I want that in green. So f of x, so we're going to have 1 minus 0 from the right squared over 0 from the right. Now, if I square something slightly to the right of 0, well, that's still going to be a very small number that's close to 0. And if I do 1 minus that, it's still going to be positive. And square root in a positive number will give us something positive. And 0 from the right is going to be positive. So positive over positive is going to be positive. So this function will go to positive infinity. Now, we can use the fact that we know this function is odd or has symmetry about the origin to see that the limit as x approaches 0 from the left is going to be negative infinity. Since we would be plugging in numbers closer and closer to 0, but that are negative. So using the fact that it's odd, we can just go ahead and do that in one step and not have to go through those same steps as we just did. All right. The next things we want to do, which are steps 5 and 6, are to determine where the function is increasing and decreasing, as well as find any maximums or minimums we may have, and these should be local. All right, so for this, we're going to need to figure out what y prime is equal to, so let's do this on another page. So again, y is equal to the square root of 1 minus x, let me write that a little bit better, 1 minus x squared all over x. So to take the derivative of this, we're going to need to use quotient rule. So remember, quotient rule is low d high minus high d low all over the square below, where those d's are supposed to be derivatives. And now I'm going to rewrite the square root as a half power. So 1 minus x squared to the 1/2. Right. And then minus these in the opposite order. So 1 minus x squared, square rooted, then d by dx of x all over what we have in the denominator squared. Now the derivative of 1 minus x squared to the 1/2 power, we need to use power and chain rule. So it's going to be 1/2, 1 minus x squared. Now to the negative 1/2 power, and the derivative of the inside of 1 minus x squared is going to be negative 2x. And the derivative of x is just going to be 1. Now we can use a little bit of algebra to simplify this down to negative 1 over x squared times the square root of 1 minus x squared. Now notice that this will never equal to 0, so we can't find any critical values that way. But we could possibly have something when we set the denominator equal to 0. And doing that would give x squared is equal to 0, or 1 minus x squared is equal to 0. But that tells us x is equal to 0, or x is equal to plus or minus 1. And so we can get rid of x is equal to 0 since our original function is undefined at this point. And we can get rid of x is equal to plus or minus 1 due to the fact these being endpoints on our domain. So we really don't have any critical points for this one. So let's go ahead and just write y prime down. So again, that should be negative 1 over x squared times the square root of 1 minus x squared. Now, actually looking at this, you might notice this is going to be strictly less than 0, since x squared is always going to be bigger than or equal to 0, and the square root of 1 minus x squared also has to be larger than or equal to 0. And since we have that negative in the numerator, it will always be negative. Or you can go about how you would normally solve for these to see that as well. But we can just kind of make that little observation and say that our function will always be decreasing, or y prime is less than 0 on our entire domain. So negative 1 to 0, union 0 to 1. And then that tells us y prime is strictly larger than 0, or increasing never. All right. Now the last thing they tell us we should do before we actually start graphing is to find where our function is concave up and concave down, and any points of inflection we may get. So we need to know what y double prime is going to be. So we have y prime is equal to, so let's go ahead and use quotient rule again to take this derivative. So we'll have low, which is x squared times 1 minus x squared minus, or times the derivative of -1 minus them in the opposite order, so -1 times the derivative with respect to x of x squared times 1 minus x squared all over what we have in the denominator squared. So that would become x to the fourth times 1 minus x squared. And normally when we get rid of that square root, we would need to put absolute values here, but we at least know on our domain that will never be less than 0. All right. So first, the derivative of -1 is going to be 0. So this entire term here is 0 also. Here, these negatives cancel out. And now we just need to use product rule to take the derivative of x squared times the square root of 1 plus x squared. So I actually need to just write that down here. So d by dx of x squared times 1 minus x squared to the 1/2 power. So this is going to be, so remember, product rule says take the derivative of the first, multiply it by the second, and then add it in the opposite order. So we're going to have 2x 1 minus x squared to the 1/2 power plus, and I'll need to zoom out a little bit. Now it would be x squared times the derivative of 1 minus x squared to the 1/2, which is going to be 1/2 times 1 minus x squared, now to the -1/2, times the derivative on the inside, which is going to be -2x. So we're going to replace this with that. And once you do that and do a little bit of algebra, we can rewrite this as 3x, so this is y double prime, and that should have been double prime up there, is equal to 3x squared minus 2 all over x cubed times 1 minus x squared to the 3/2 power. And so we're going to need to go ahead and set this here equal to 0. And doing that will tell us, and let me actually do that in green instead. So that will tell us we need our numerator to be equal to 0. And solving for that, we'd get x is equal to 2/3. Oh, this should be squared. 3x squared minus 2. Yeah, so actually we end up with this being x square root of 6 over 3. All right, now we can go ahead and look to see where the function is undefined also. So we want to make sure our denominator is equal to 0 at certain points for possible critical values. So again, that's going to be x cubed is equal to 0, and 1 minus x squared is equal to 3/2 is equal to 0. But for similar reasons over here, we will end up where these don't actually give critical values since it's either undefined or endpoints. So the only point of interest we actually get out of this is x is equal to the square root of 6 over 3. All right, so we have y double prime is equal to 3x squared minus 2 all over x cubed times 1 minus x squared to the 3/2 power. Now let's look at where the function, or where our second derivative is strictly larger than 0 or concave up. And this is going to be on oh, and actually, let me go back real fast because I forgot one thing. So it shouldn't just be x is equal to that. Since it's squared, it should be plus or minus this. Since we should have two solutions on our interval. All right. So we can go ahead and now actually put that this interval here where it should be up should be negative square root of 6 over 3 to 0. And then union square root of 6 over 3 to 1. And our function is going to be concave down, or y double prime is strictly less than 0 on the rest of our domain. So negative 1 to the negative square root of 6 over 3. Union 0 to the square root of 6 over 3. All right, so now the only possible point of inflection that we got was x is equal to 0. Or actually, did we? No, our possible points of inflection were those two. So let me do that below. So we had x is equal to negative square root of 6 over 3, and x is equal to the square root of 6 over 3. So to the left of negative square root of 6 over 3, the function is concave down. And from 0 to the square root of 6 over 3, the function is also concave down. And to the right of negative square root of 3 to 1, or to 0, the function is concave up. And after the square root of 6 over 3, the function is also concave up. So both of these are points of inflection since we have that change in concavity. So let's go ahead and zoom out a little bit. And now once we did this, they said we're good to go ahead and actually sketch our graph. So let's plot our intercepts, which end up being negative 1 and 1. So negative 1 and 1. We have an asymptote at x is equal to 0. And to the right of 0, the function should be going to infinity, and to the left, the function should be going to negative infinity. We have no maxes or mins, but we at least know the function should always be decreasing on our domain. And we have points of inflection at negative square root of 6 over 3 and square root of 6. Oh, let me go ahead and put that underneath. Square root of 6 over 3, like that. So both of these are points of inflection. All right, so now let's go ahead and start graphing. So let's start to the right of this function here. Or actually, let's start at x is equal to 1. So we know from square root of 6 over 3 to 1, the function needs to be concave up. So that means it's going to look something kind of like this until we hit here. And then after that, it's going to be concave down as we approach infinity. Something kind of like that there. Or actually, I think I have the up and downs for this a little backwards. So yeah, I went ahead and wrote them down in the opposite order. So actually this should be concave down from 1 to our point of inflection, and we go up like this, and then we just go ahead and change these really fast. So this should be down, and this should be up. So if you would have did the algebra, you should have got the opposite of what I had said in this step here. But at least when we started to graph it, it really wouldn't have made much sense for what our function was going to look like. So that was an easy way to catch that. All right. And then next, when we start from negative infinity, we're going to go into our point of inflection, and on this part, we know, so from negative square root of 6 over 3 to 0, it should be concave down. So it should look something like this. And then after this point, it's going to be concave up. All right, so we can go ahead and go back and possibly put in what these 2 points are or the points of inflection, but since we're just sketching it, I think this here is sufficient enough.